which is the tradition of this academy. And the second tradition is that President gives a presidential address, which I'll do it now for the next 40 minutes to tell you about a subject in which I am involved, and then we'll proceed with the program. And internal forces which are there like in violation. And the one which I've highlighted is the discussion I'll focus on in the next 40 minutes. Effect of shear, electrical fields, and very simple, even gravity. So I will try to, so before I do that, this background, I have a great secret in really doing the right shear. And the reason is that the main structural component of chocolate is a cocoa butter. And this is nothing, this is a fat, which is a multi-component lipid system with mostly 4 fatty acids. Some are 2 here and crystallize, you produce crystallites, it has a different texture than when you just cool the cocoa butter. So I just wanted to leave this because there are many other examples in the day-to-day life which depends on shear-induced crystallization. And some of them which you might be using is margarine. This is crystallized in an otherwise amorphous matrix, which is done using shear. Of course, you have all this. I'm not supposed to give a name of this. I'm not advertising, but this is just on the web. I took this picture that a lot of these products like soaps and all, green soaps, have shear-induced crystallization, and that adds to the texture. The reason we got interested is that in the last 1 or 2 years, I have been looking at shear-induced crystallization, which is very unusual. So we have a surfactant system where it is in a fluid phase, but much above the freezing temperature. But when you shear it, you get reversible, you get crystallites which are reversible, which means if you remove the shear, they melt away. So you have shear-induced crystallization, which is reversible and it occurs above the freezing temperature, which does not happen in many systems. So it has very interesting physics issues and chemical science issues. Why is it happening? So if I get time, I'll say a little more. But first, let me move on to the first example I want to discuss about active particles, or in these days it is also called active Brownian motion. So in today's talk, we will be discussing 2 cases. First, where the energy input is driving the system out of equilibrium. It can have 2 ways. One, where you feed the energy locally at the level of each particle. So each particle is given energy and it is doing the activity. For example, in motors, and some examples I'll take. Second one, you give the energy at the boundary, like in a shear flow, like churning when you do in a simple way in a kitchen. That is shearing the food. So these 2 examples I'll take, and examples of active matter in the last 10 years are many, which are exciting number of issues like molecular motors and biofilaments, collection of motile microorganisms, animal, fish and bird flocks. I'll show some beautiful pictures taken from the net. And last one, chemical or mechanical indicators. So how you can study all this active Brownian motion in the lab. And here the direction of self-propulsion is decided by some anisotropy. So there are many interesting issues in this field. When, for example, the number fluctuates when you have this active particle, which is not like square root of n, which we all know, but it goes like n. You have non-equilibrium of phase transitions. You have pattern formation, which I'll show 1 or 2 examples. You can have wave propagation and sustained oscillation, even in absence of inertia, and very unusual rheological properties. So this is an example which you all know is an active matter, is a E. coli, and it has a run and tumble dynamics, which you can see that it tumbles, runs. This is an example of active matter. And so this is a snapshot, larger picture of this. And this is another collective motion of variety of these big objects, small objects, which I have taken from the net and in this review article. So you can see that in the pond, you will see these fishes forming this collective motion spontaneously. You see this beautifully starting flock in the sky when these birds fly. You will see this locust, they form again very beautiful pattern. And then you might have seen if you go to a forest, that these are called ant mills. They keep on rotating because the queen ant has been removed and they don't know what to do. They go berserk, they keep on rotating. After a number density increases beyond a point, these are called ant mills, and these are the locusts which again rotate. They form the ordered pattern above a certain density. Now this is the example I'll discuss in the first 5 to 10 minutes from my lab. So we are looking at a self-propelled particle. So if you see, this particle is moving. I should have the pointer. So this particle is a brass rod. I'll tell you the dimension. It is moving on a substrate, and this one is moving in a medium made of the steel balls. So what is the experiment and why are we interested? So this work is done with the student Nitin and my colleague Shriram Ramaswamy. So what we are interested is this particle, just one particle only, very simple example. How does it move? So it's a very simple experiment. You take this particle, which is polar, which means it has a head and a tail, and you put it in a plate, and this plate you can cover it and put these particles here and slightly shake this plate. So very simple experiment where you shake the plate and then the particle starts moving. Only if it is polar. If it is non-polar, it does not move. The reason it moves is it has a head and tail. So when it comes back to the surface, it gets a net momentum and it moves. So it moves exactly like if you don't know what it is from a distance, it moves like bacteria. So we can define how much we are shaking, what is the acceleration of this plate with respect to gravity, this number I'll quote, and this is something we can get some very interesting physics. So why are we interested? So here, if you have a particle which is just a bullet, very cylindrical rod, if you keep on shaking, nothing happens, it slightly ziggles and it has a diffusive behavior. But moment you have a particle which has a polarity, head and a tail, you can see the size is different, it moves. So this one is about 3 to 4 millimeters and diameter is about a millimeter. So this moves when you are shaking vertically. So these are called self-propelled polar particles. Self-propelled means they are taking the energy from this vibrating thing and moving. Now you will ask, what is so interesting here? Now here, okay, this is another example. If you change the shape of this projectile, you can see that it moves like tumble, run, and so on. Somewhat like E. coli. So if you have the velocity plotted, you will see the two types of motion, which of course, as physicists, we can quantify as the probability of the velocity. This is centered around 0. This is the tumbling motion, and this is a huge velocity when it moves. So depending on the polarity and the acceleration you give, you can have the self-propelled particle. So now we are interested how this particle is moving, what is the statistical mechanics of this. So the reason we are interested in is that when we look at this motion, the particle is not going only forward. It is actually going back and forth only if there is a medium present. And the medium are the steel balls which are apolar, which do not move. So this is something where you have this negative direction. Now this is very unusual. Usually the particles go without the medium in the forward direction. Now why is it going back? Now for this gives rise to a very interesting set of questions in non-equilibrium statistical physics, that why do you get negative velocity events? And this is actually a very interesting question in the last 10 years, 10 to 15 years. That usually we know that if you have a hot block and a cold block, which you know, for example, in the kitchen, you know that the heat will flow from hot to cold. We all know that. But can you ask yourself a very simple question? is there a probability that heat will flow from cold to hot, which we never consider. So these are called rare events or the entropy consuming events, and these events, of course, on a big time scale, you do have hot to cold. So we are not violating any second law of thermodynamics, but the question being asked is, what is the probability that on short time scales, you can have this reverse events? And this can occur in many situations. For example, if you pull something in this, you will think the particle will go in this direction. But at short time and for small degrees of freedom, the particle can go opposite to the force. This is something which you don't think, but this probability is finite. So we are interested in such probability events. And there is a very deep theorem in non-equilibrium physics, which is somewhat as deep as the fluctuation dissipation theorem in equilibrium stat math. Namely, that if you have this entropy which you produce by these events, you can define a quantity. I'm sorry to show little maths, but this is just tells you how powerful the theorem is. It tells you that the probability of having entropy consumption over entropy production over consumption is independent of the system. It is such a theorem which does not depend on the details of the system. Whatever non-equilibrium driven system you have, this theorem says that if you wait long enough, the reverse events are very few, and if the value of that event is large, again you don't get negative event. This is what intuitively you will also think. Now this theorem is called Colloidal fluctuation theorem. So we were interested to see if it is verified in a polar particle experiment, because it has not, the validity of this theorem is still people are working on it. So there is another thing which comes in many parts of physics and engineering called large deviation function. So this is a function which tells you what is the probability of rare events, how much it can go positive, how much it can go negative in the tape. This is also like election results. When you do election results, you are really interested in the large deviation events, because the center one you can predict how people will vote. But these are the outliers which really cause all the surprises. So this is again a large deviation function which is defined by f of tau. So the purpose of these slides is not to give you the details, but to tell you that there are quantifiable quantities from the experiment which we can verify, and we show that if you do these events which we have described, you do probability distribution for this entropy production or the velocity, which is highly non-Gaussian, and this is very unusual. And from this we verify that the fluctuation relation, which is derived in the context of non-equilibrium physics, is indeed verified in these examples. This is a collapse with all this way we do it. So this is just to tell you that even a single particle moving has very interesting physics, and we want to learn what all these driven systems can do. So the large deviation function, which is usually quadratic, is very unusual in this experiment. It shows a kink, and it turns out this kink was predicted theoretically but never seen experimentally. So these systems, what we have studied, does show a very unusual distribution deviation function, which is very different from a quadratic expected for a Gaussian probability. So let me, this is seen for molecular motors, but now you can ask, if I put many of them in a track, what happens? What is the experiment, why is it interesting? Now this is the example which mimics the, when you have traffic and so on. So there are many models which try to study this, or the ant trails which are moving. Now what happens here, if you wait long enough, they all do condensation. They will start separately, but collective behavior in the end, they will move as one block. So this is called, in the context of this, Bose condensation. It is not the usual Bose condensation, but it is a condensation of the front space in front of the particle which condenses. So again, there are very interesting predictions which we are verifying in these experiments. Now this is the picture I took from the net, where what is the collective behavior of active particles? How do they behave when you put many of them? You must have seen these flocks in the sky, and all these issues are very important. Now this paper in Science 2006 does on this locus, which is the desert locus, and they show that above a certain density they have this corrective behavior. And if you read this paper, it seems it is very critical to understand the ecology of the forest when these locus are present, which is really not a welcome thing. But people are interested how this locus behaves so collectively as if they are thinking about and following each other. So here they show what I said, this kind of collective behavior in these ants. And this one is something, a topic which people are still trying to understand. This collective behavior of many of these objects. What is the physics? What is the minimal physics? Sorry, I should be careful. What is the minimal physics which can capture? Not the details, how the locus thinks or works, but collective behavior, how does it come? And this is what we have done the experiments. So we put many of these polar particles. If you don't have a medium, nothing happens. They move randomly. It's a disordered phase. But with the medium, you can see that within few seconds, they all become in a circular motion. So this transition from a disorder to an order is something which we are trying to understand in the context of this collective behavior. So we can quantify this in terms of order parameter, and we can show that within few seconds, when the medium is dense, they all move in the same direction. It can be one direction or the other direction. So collective behavior is again something which is very interesting. So it does not happen if the medium is low density. Only it will happen when the medium is high density and you have enough of these polar particles. So the second example I move now from the active particle to the system where you are giving this shear. So this is an example of colloids. So this example is something, can you click on this? These are the colloidal particles which are about a micron in size, and put them in water and look in confocal microscope. They will have this free Brownian motion, or depending on the density. And depending on the density, you can get a liquid-like behavior and a solid or a glass. And if you look at it in the visible light, you see beautiful colors. This is exactly silica opal which you buy in the market. Silica opal is a colloidal crystal of silica particles which is arranged on a lattice. And the black diffraction of visible light gives you this beautiful color. So all this TMV, tobacco mosaic virus, all this science is same. So these are the colloidal crystals where you get in black diffraction because of visible light. So now here in these systems, these particles are made of a polymer whose volume changes with temperature. So when you cool them, it is a much bigger particle. When you heat it, it shrinks. And this allows you to go from a fluid-like phase to a crystalline-like phase. Same system. So you can go this transition where the particles are free to move, and then they suddenly become beautiful face-centered cubic lattice. So they get colloidal, they form a crystalline lattice. Now here, when they form a crystal, it is not a single crystal. You can have these crystals which are few micron big, and this particle is 1 micron, so the crystal can be about 10 micron to 20 micron, and there are many of them in the sample. But now if you look at the grain boundary between these two, this grain boundary is something which is almost like a glass. So so next 5 minutes, I'll tell you what is exciting about these crystals. Because there is a lot of science to be understood how these grain boundaries behave. And this is the work which will appear in probably 1 or 2 months in PNAS. So here, last year we showed that if you take these colloidal crystals and focus your attention on this grain boundary, means the atoms between the two crystals, because all the material you use are polycrystalline. This is a system not in a brass or a copper, but a colloidal crystal. It is a model system where you can look at each particle in a microscope and follow in time, which you can never do in an ordinary brass or a copper or steel. So these are beautiful systems which allow you to understand the physics and hopefully you can learn some message for the engineering material. That is the goal. So last year we showed that this grain boundary is very disordered, which is not surprising because you have one crystal and another crystal, and this grain boundary has all the properties of a glass. It is a glassy material, it is a solid, but a disordered solid. And this has very interesting ramifications on the behavior of grain boundaries when you shear it and so on. And this is what we have addressed. So the grain boundaries are really decide the strength of the material. So all the material which we use in our life has this grain boundaries, and the idea is to enhance the material property. And this material property is done by alloy. For example, gold. When you take 24 karat gold or 22 karat gold or 18 karat gold, essentially you are alloying with something and you are changing the property of gold. The second one is you do the mechanical treatment and make the grains grow at the expense of something other grain. So this is the grain boundary engineering, which is very critical for application. So we want to understand the behavior of these grain boundaries when you shear a crystal, because this is something we can learn from the first principles what is happening. So we do these experiments. There are a lot of open issues. We want to address that how these grain boundaries behave, what is the connection, how they rough up. And here it is a multi-land scale problem because things are happening at a single atom level, but grain boundary is big. So how do you go from one land scale to another? So in colloidal crystal, by cooling at a different rate, you can get different grain sizes, and we can look at the function as the material property as a function of grain size. So this is a very beautiful system which allows you to do very fundamental science which may have implication in engineering material, which is like steel or copper or brass. So that is the goal of these experiments. So we can identify grain boundaries by appropriate mathematical constructs, by looking at the neighborhood and how they are correlated, and then we can find out how these grain boundaries behave when you shear it. Now this is a very beautiful experiment set up by Dr. Rajesh Ganpati and GNCSR. This is a very difficult experiment. Here what he has done, he has set up the whole rheometer on a confocal microscope. So when it is being sheared, you can do confocal microscopy. There are very few setups in the world which can do that, and this allows us to do the shear and look at the microscopy at the same time and get very detailed static and dynamic properties. So the idea is the grain boundary between these two, how do they behave? Since I'm not going to give detail, I'll just tell the gist of these experiments, which may have some implication in engineering materials. So the idea is that when you take, so we are now shearing in a oscillatory manner, and this is the grain boundary we are tracking. So what we find is that a grain boundary, let's say normal is this, and this is the shear direction. This is very different if the grain boundary is parallel to the shear. So here the grain boundary normal is this way, which I call the grain boundary perpendicular, and this is grain boundary parallel. So these experiments establish for the first time that these two grain boundaries are very different. When the grain boundary is perpendicular to the shear, it makes it very rough and the grain grows. If it is parallel, not much happens. Now this kinetic roughening, which is anisotropic, has interest because the grains will grow only along the shear direction. So this is something which we quantify because we plot the interface fluctuation as a function of time, and how this interface fluctuates as an information that one of the interface is very broad and fluctuating, other interface is not too much fluctuating. So this is something we quantify, and to get across how we do this, only for few people who might be interested, we look at this grain boundary as if it is a surface. How does it fluctuate? You know that water surface on a trough fluctuates, so we analyze exactly the same way. We look at the capillary fluctuation, and from that fluctuation spectrum, we deduce the surface stiffness. And that surface stiffness is very different for two types of interfaces. So this is essentially the essence of this result, all this data which I will not go into, but at the end of the day we show that one of the grain boundary is very rough and mobile, other grain boundary is not that. And this has implication on the grain growth. So perhaps let me come to the so we can also follow the entire crystals, and we can show that some of the crystals will grow at the expense of other crystals when you shear. So this is the first time in this literature we can see a direct anisotropic growth of the crystals under shear, which has some interesting physics. So let me not go into the details of this, but the third example which I want to discuss is colloids under electric field. Now what happens if you take this colloids and put in electric field? Now this I will tell you is also an example where you can start from some very basic physics issues and you may end up with the application. So this is something we didn't want, we didn't have application in mind, but we ended up discovering the application. Now what happens when you put colloids? These are the colloidal particles in electric field. So very simple experiment. You put these two electric field around this, put a colloidal particle and they form chains. This is called electro-rheological fluids, which has enormous applications in brakes and so on. So you can apply brakes by putting electric field. This is something well known. What is less known is the next slide. It was discovered 10 years back that if you take this electric field in this direction, the particles come in this direction, xy, which is unusual, not along the field, but perpendicular to the field. That was not known, which means the particles are going to feel each other when you apply electric field. And this is something which we studied, and you can form these beautiful crystals in when you put the electric field. So, for example, you apply a voltage of 2 volts on these two plates, and you will at 1 kilohertz, and after some time they will all come together and form a crystal. So this is crystallization under electric field in the xy direction. So what is interesting here? Now why it happens is something very interesting. Physics is called electrohydrodynamics, that you generate the flows around colloidal particle, and these flows attract each other and give you the attractive interaction. Now, this is something we studied, that if you have electric field of different frequencies, you get very different shapes of these crystals. But last few minutes what I want to spend, based on that, we thought that it might have application in particle-based diagnosis. Now, why we thought that? Now, this test is known for a long time, that when you go to a hospital and you want to get a test done, what is done is called latex agglutination test. So, for a particular disease, you know what proteins have to be detected. The antibodies of that are put on colloidal particles. This was discovered in 1956, and the first pregnancy test was done in 1957 using this method called latex agglutination test. So, what is the test? So here the idea is, you put antibodies on a colloidal particle and you put the antigen, which is in your serum or whatever you have from the patient, and when you put them together, and if it is the positive, they will all coagulate. So you might have seen in the hospitals, they mix it on a plate and they see a curd-like thing, which is agglutination, and that is called a positive test. Now this is something available for about 250 tests in the market. So there is a huge application of latex agglutination test, latex agglutination method in the diagnostic. Many tested this idea with a very simple example. We took colloidal particles with streptavidin and we took RNAs, and Raman attached the biotin to this, and we tested how much of the RNAs we can detect by this method. And second one is a commercial test which we did. So here we show that when we do this test without the electric field, we need about 1 micromolar per liter sensitivity required. we need that much of antigen, RNAs. But now if we put this electric field, from these images we showed, even at 10 picomolar, we have a huge sensitivity and very, very fast detection. So it has enhanced the sensitivity in tens of time for this diagnostic. And this we tested also for this kit which went to the market. This kit is for rheumatoid arthritis test, which is made to test a particular protein, IgM, and there are appropriate antibodies attached to the colloidal particle. And here also we could show that it has enhanced almost 500 times. So this is a very simple way to enhance the sensitivity using the electric fields. And this is a typhoid test we did in collaboration with the DRDO people. You know that typhoid is a Vidal test. All of us know that, which is done after 1 week of test. You know, you do 2 tests, but it is never, people don't wait and start antibiotics. In this, what we showed, this lab developed the right antibodies for this, and we showed that with our method, you can detect much, much less quantity of this antigen, and you can detect the typhoid. And this is been applied for a patent by them, and they want to market it. So the last part, which I discussed in the last few minutes of this driven matter, is to show that electric field does many interesting things to colloidal particles because they are electric, and we can use this effect, this force due to electric field, to make some interesting applications. In the last 2 minutes, I want to discuss this because this is a really high school experiment, and it started as a high school project. So the project was to study the steel ball sedimenting in a liquid. We all know this high school experiment for Stokes' law, that when you drop a ball, it will attain a steady state. And we all know this is used to measure the viscosity of a liquid. We all know that, high school. So Aditya, actually he wanted to do this project not in water, but some unusual fluids. And unusual fluids we were studying at that time are these viscoelastic gels, soap solutions essentially. Essentially it's a soap. You just put 2% soap in water and that's a viscoelastic gel. The idea was what happens if it falls under gravity. So we all know if it is a simple fluid like water or glycerol, you get a steady state because the drag force is balanced by the weight of the particle and the steady state velocity, we know how it behaves. This is really high school. We can measure this and get a right viscosity of the fluid. But now, what happens? We take a gel, which I will not discuss, but now when they drop a steel ball, you can see that the steel ball velocity is extremely unusual. It has a huge velocity, this is the steady state, but it never comes to steady state. So it has oscillations of 2 types of frequency. So if you see highly damped oscillation, but against spurts. This was never known. A simple problem which Stokes did in 1890 or something, I don't get the date from, has not looked at viscoelastic fluids, what really can happen. And another experiment, when the conditions are slightly different, you will again see lot of oscillations. When I expand, you will see it, and you will see a beautiful time pattern. So if you plot the data for one particular gel, you will see that when the diameter of the ball is small, 4 millimeter, these are the balls made by the cycle shop sellers. If you go to cycle shop, you can buy these balls in about 10 rupees, many of them. And you can get different balls because cycle parts have different ball sizes. So moment you make the size 7 millimeter, you start getting this oscillation. And you can see that you get beautiful oscillation within a buzz, but what is unusual is really this periodicity. So you have 2 time scales in the problem, which is what I have written here, I am not going to. And question was, why is it happening? And I should tell you that this problem, something occurs in neurobiology all the time. This is called a busting instability. So we saw the literature, but of course that physics is very different in neurobiology. So what Shiva and Raman did that was, we went to the basics, wrote the Stokes equation. Now the idea is when a ball is moving, it will align the micelles. So it will move faster. When it moves faster, the micelles which are below, they will resist and they will slow it down. Resist, slow down, resist, slow down. And this is really what is happening. But this has to be quantified in a model, which they did that, Nitin also was involved. The velocity is the usual velocity plus a effect which is coming from micelles. And this effect, when you quantify it with these nonlinear equations, does produce something what we are seeing, but not exactly what we are seeing. It has a busting instability and a damped oscillation. And this is something very similar to this pacemaker neurons people see. Within the burst you see huge oscillations, and again this burst keeps on repeating in time. So it is a similar mathematical model which is done for neurons. So this is the beauty, right from 7 millimeter steel balls in a normal soap solution to the neuron. The physics is cutting across all these landscapes, and we are trying to understand that. So now when you put a bubble, what happens? This is again which these kids played around in the lab, and we realized again it has instabilities. When you release a bubble, you will see that bubble shape is like a balloon, and when it will change its, you can see these oscillations. You get these huge oscillations in the lab, and you will quantify them, and again this is something we have not understood. There is no theory right now, and there is no such experiment in the literature which has been done and the theory which captures it. So again you see the beautiful shape oscillations and so on. So this is again something very interesting which gives us many thoughts what we have to pursue. So let me close this discussion of this morning to tell that the purpose of this address was to look at active matter, a few examples, and I tried to show that it is an emerging paradigm for very exciting non-equilibrium physics which cuts across many disciplines, chemistry, material science, engineering, and so on, biology. And what we hope is that the lessons learned from mechanical limitations in the active matter may help to understand collective behavior in other active systems. That is the hope, and we think we are on the right track. And in the second example, when you do shear soft matter, we realize that it's not only relevant for many applications, but also very fertile ground for non-equilibrium Stackman phase transitions and so on. So this is a story which is incomplete, it's going on in the lab, and we hope that we'll have many interesting things to talk about. Thank you very much.